Thank you very much, and thank you to Zoja for inviting me to give this talk, even though she's a co-author on this talk. Okay, so what I'm going to be doing is following on quite a few of the messages that we've been having, particularly yesterday, for those of you at the workshop, that microstructures matter and that we need to start thinking holistically about the messages that our rocks are trying to tell us. Okay, so this talk is basically a plea to everybody to start thinking about microstructures. Now, how do I describe what I do? Well, I see myself as a forensic petrographer, right? This is a person who deduces rock history by analysis of microstructures, okay? So what the sort of basic process is primary observation. You need to look. And not just look, but see. You know, you need to see what the rock is trying to tell you. And you've got to document and measure everything that you see in the microstructures. And then, you know, Donald Rumsfeld was absolutely right about this. Known knowns are things that we know about, right? And material science has been going on for centuries. They actually care about understanding what controls microstructure, because if a plane falls out of the sky, it's their fault. Okay, these things matter. So they have been working really hard, and they've got a huge understanding of the thermodynamics, the physics, the chemistry of what controls microstructure, because that's what they do. That is their job. So we delve into the material science literature. Now, if we find a known unknown, something we're really scratching our heads about, that isn't explained by the material science literature, the best way to do it, to understand it, is to isolate variables that could possibly be influencing what you're seeing and work out what it is that's controlling it. That's a very good thing. But of course, there are always unknown unknowns. These are the things that you don't know that you don't know. And the best way to tackle that is to keep an open mind, to go to conferences, to listen what people are saying, and to visit as many igneous rocks as you possibly can. The best geologist, the best petrographer is the one who's seen the most thin sections, okay? So once you've done all of that, you can piece together all the observations that you've got. You can match it up with chemistry, you can match it up with field observations, you can match it up with geophysics, you put everything together to understand what your rock is telling you. So I hope that, you know, in this next diatribe, before we all go for lunch and breathe a sigh of relief, that you will come to see that this might actually be a useful way forward. So I'm going to concentrate on the UG2 chromitite. This is work I've been doing with Zoja, and Ilya Vexler was helping to get us some samples. So the basic question is, what can we say about its origins purely from microstructure? Forget the chemistry. Let's just look at microstructure. So this is just a nice thin section here. These little holes here, this is where chromite grains have been plucked out during the polishing of the section. So there's actually a lot more chromite there that you can see. Now, the big question is, did this grow by in situ nucleation and growth? Or are we looking at an accumulation of crystals that were nucleated and grown elsewhere? And if it was an accumulation, are we looking at single crystals accumulating? Are we looking at clusters accumulating? And post-accumulation, how much growth might there have been? Or are we looking at a mixture of all these different things? So these are all the sort of the questions that people are arguing about, losing sleep over. Well, some people lose sleep over it. What can we do to try and shed some light on this big problem? Now, the first thing we need to get to grips with is that it matters whether the intrusion we care about is open or closed. And that's because that affects where nucleation can happen, because nucleation requires an undercooling. So if we've got a closed system and it's quite a deep intrusion, you've got this nice diagram here. This is from a paper by Tony Morse, but this was initially thought of by Neil Irvine in the 70s. If you dilate an intrusion, or dilate the crust by intruding a lot of magma, then you're splitting the geotherm, right? And the geotherm is basically this line here, and then it relaxes very quickly. So you get something like this, and there's a magma temperature there, and then it goes down like this. What that means is that the undercooling at the floor is smaller than that at the roof. So you're predominantly going to be nucleating things at the roof. Not only that, if you've got this instantaneous injection of magma, you lose this undercooling very quickly as well, because you've got an awful lot of crystals accumulating on the floor, and that makes a sort of boundary layer that it's difficult to diffuse heat through. So if you've got a closed system, you are only going to nucleate things in situ on the floor in the earliest stages. Once it's been developing for a long time, you know, you're halfway through the crystallization, most of that nucleation is going to happen at the roof. If you want to keep repeatedly nucleating things on the floor, you need an open system. You need a constant influx of superheated magma that gets chilled on the floor. And in fact, this could be the answer to that really nice talk that just preceded mine. When you've got this evidence of rapid growth, big delta T's, maybe that's because you had some superheated magma coming in. That open system, Setil was an open system, and that might be what we're seeing. Okay, so a prime example of in situ nucleation on the floor of an open system is given by these really beautiful dendritic olivines. This is harrisite on rum, and that is the hand of Bob Hunter. So Bushveld, again, an open system. Setil, an open system. So we do have the possibility of the incoming of superheated magma and nucleation on the floor. But if we're talking about something like Skaergaard filled very, very quickly. I don't know how quickly, but it was essentially, once it had filled, it was behaved as a closed system. So the only evidence we have for in situ nucleation on the floor of the Skaergaard is preserved right at the bottom in the lowermost couple of 100 meters. So we've got this example here of in situ nucleation near the floor of the layered series on Skaergaard. Oops. Right, so what can we do with these two end members, crystal accumulation versus in situ nucleation? What do they look like in the field? Well, I just run through some sort of nice, simple examples from Skaergaard. So if we've got crystal accumulation, we're basically looking at a sedimentary system. This is a magmatic sedimentology. So what we see are nice channel structures like here. If we zoom in a bit closer, this is my scale bar that frightens you off from making difficult questions. We can see truncation of layering. We've got an erosive thing going on. We can see evidence of slumping. Skaergaard was sitting in a tectonically active environment. It kept getting rattled around by earthquakes, and that slumped things. And we also see evidence for truncation of layering. We've essentially got cross-bedding here. This is clearly a dynamic environment where crystals are being moved around, rearranged, and accumulated very, very nicely. And there's Jens for scale. And we've got these beautiful modally graded layers. Again, this can only happen in a dynamic environment. But critically, this kind of fluid dynamic excitement is dependent not only on intrusion size, you need it to be cooling relatively slowly, but shape. And the great thing about Skaergaard is that it was a box. It had kilometers high vertical walls. It had convection. It had stuff falling off the walls. It was a really, really dynamic environment. And you won't expect to see that kind of excitement, if you like, in an intrusion that's essentially a thin sill like Bushveld. And this is where I'm jealous of Rice. He's got the most amazing collection of field photos, and I don't have any. But we don't see that kind of evidence for cross-bedding, truncation of layers, channel formation in the Bushveld. And I think that's because the fluid dynamical regime was a bit different due to the shape of the thing. It didn't have these steep vertical walls. Okay, so that's clear evidence for accumulation of crystals. What about field evidence for in situ growth? Well, the most obvious example of this is when you get dendritic horizons like the harrisite on rum, and this is a loose block from near the floor of Skaergaard. I don't know exactly where it's from, but we can see there's lovely elongate plagioclases, and then these beautiful single crystal dendrites of pyroxene that are clearly nucleating on this horizon here and then growing upwards along a gradient of either temperature or composition. Okay, we've got directional growth of elongate grains. There's another example here. This is the very famous perpendicular feldspar rock, also of Skaergaard, where you can see this directional growth of these little plagioclases going down the thermal or compositional gradient. Now, we've got recent models of directional growth, of in situ directional growth, that involve polycrystalline monomineralic chains of chromite. And well, I think he's changing his mind now, but the published mechanism for this is this process of Ian Campbell's, which is heterogeneous self-nucleation. And I've put that in inverted commas here because it doesn't work. Right, so nucleation, primary nucleation is what happens when you haven't got any grains of that particular phase that you care about. So they're the first crystals to form, and it can be either homogeneous or heterogeneous. Homogeneous is when the nucleation just occurs in the bulk magma. You need a really large undercooling for that, and you need no possible substrates on which it could nucleate. So homogeneous nucleation is actually quite a big ask in a noisy, dirty magmatic system. So heterogeneous nucleation is going to be the norm, and heterogeneous nucleation has got a smaller overstep that's required compared to homogeneous because it borrows a substrate. It reduces the thermodynamic barrier to nucleation by using a substrate. And that thermodynamic barrier is reduced even more when there's some kind of lattice matching between the phase that's nucleating and the substrate. And that's generally called epitaxy. And the beautiful example of that, which you will see almost everywhere in mafic rocks, is the epitaxy between clinopyroxene and titanomagnetite. So Julia Hammer's done some absolutely beautiful work on this, and she shows that, yes, there is a crystallographic relationship between those two minerals, and it's very, very easy to nucleate your magnetite on the clinopyroxene substrate, so that's where it prefers to do. Critically, heterogeneous nucleation always involves two phases. And that's because when you're trying to nucleate a new grain, there will be this thermodynamic barrier, and this idea of heterogeneous self-nucleation is where you have a substrate of the same phase and you're heterogeneously nucleating another grain of that same phase on it. It will always be easier to simply continue growing that substrate than to go through all the trauma and work of nucleating a new grain. So it simply doesn't work, okay? It's not physically plausible. So that's what things look like in the field. What about thin sections? Now, if you've got crystal accumulation, we've got magmatic sedimentology, you generally tend to find your rock looks like a sandstone almost, if you're really lucky. So this is one of the plagioclase-rich layers from the Skaregard, and we've got clasts of plagioclase and with interstitial material here. This happens to be quartz, and we've got interstitial albitic overgrowths. And you can see grain boundaries are formed by the juxtaposition of growth faces. Right, they're just grains, nice euhedral grains, and they've come together and they've solidified. Very, very characteristic. You can also commonly get fabrics, lineations, foliations, and that's because these particles are being moved around and reorganized by magmatic currents. Just a sedimentary example. So this is just a quick example from the Skaregard again. We've got these elongate plagioclases in these layers, which are formed by magmatic density currents coming down, and the plagioclases form these beautiful lineations. But if we've got in situ growth, in situ nucleation and growth, you've basically got the nuclei there, everything's static, and the grains are just growing until they impinge. And that gives a very characteristic microstructural signature in that the grain boundaries bear no relationship to growth faces because they just grow until they impinge, and they're randomly oriented usually. And not only that, but you tend to get these undulations as they impinge together, and you get these melt-filled lenses. So this is a nodule, an enclave, a crystalline enclave that was entrained by an Icelandic lava flow. So it's been, the solidification process has been quenched as it was brought up. So we see the grain boundaries bear no relationship to growth faces, and we've got these lenses, and we've got randomly oriented grains. And sometimes in those growth lenses, you can melt lenses, you can see little, they're just starting to be filled in with another phase. So this is two plagioclase grains, that's glass, and there's a little bit of clinopyroxene just growing in there. And you can sometimes see other things. So these, sometimes when you get these crystalline nodules, they've got melt films on all the grain boundaries. You could argue that those melt films are there because the thing disaggregated as it was depressurized on the way up. But things like this and the previous slide demonstrate that these lenses of melt, if you like, these grain boundary films, irregular grain boundary films, are primary because you've got other phases starting to nucleate in them. So this is just sensitive tin plate in with the cross polars. just really emphasizing that irregularity of the grain boundaries. Here they are, they're going all over the place. They bear no relationship at all to growth faces, and you get a lot of included grains. So there's an included grain there, which is probably an optical continuity to that. So you can imagine this grain boundary is really, really highly irregular, no fabrics, no nothing at all. So this is just comparing the two. So on the right here, we've got a dominance of grain accumulation. This is a sedimentary rock, if you like. We've got nice euhedral plagioclases. On a bigger scale, there is a foliation in this rock, and you've got grain boundaries formed by these euhedral grains coming together. Whereas on the other side here, this is also scaregard, but this is stuff that grew on the wall, which is all in situ growth. And you've got no fabrics, you've got a lot of compositional zonation, you've got a very wide range of grain sizes, because if nucleation is going on continuously, the little grains are the ones that have only just nucleated, or there was a higher nucleation density before they met their neighbours. Whereas here we've got current sorting, the grain size variation tends to be much smaller. And what else have I got? Irregular grain boundaries, no preferred orientations, etc., etc. Now, what's quite amusing is that Alex McBurney, who is one of the giants in scaregard petrology, used to like drawing diagrams. This is one of his papers here, McBurney and Hunter, 1995. And you can tell it was him because he always drew a little man in his diagrams, and you have to hunt for him. He's called Derek Bostock. And there he is, and he always smokes a pipe, and he's got a beard. Okay, so on this example here, you can see he's actually unknowingly drawn something that shows microstructures typical of growth to impingement. You've got these beautiful wavy grain boundaries, you've got lots of included grains, you've got a wide range of grain sizes, no fabric, whereas on this side here, you've got beautiful fabrics, grain boundaries defined by the meeting of euhedral growth faces, etc. So very clearly, distinct microstructures. But what can we do knowing all of that with the chromitite? Now, the chromitite doesn't show nice things like that because the grains tend to be rather rounded, and we don't see, we can't really see what the grain boundaries are doing. So that preamble sort of sets the scene, but it means that we can't do a lot of the easy things with the chromitite. So now let's just go back to the forensic petrography mindset. What can we observe? Well, this is just a typical Dwars River. This is UG1 rather than UG2. Generally, these chromatites have no fining upwards. There's no modal grading either. So we don't have evidence that we can jump on for gravitational sorting, at least on the grain scale. Okay, if these were individual grains, then the lack of grain size grading would mean that there was no gravitational sorting. And we've heard a lot about this. You can see these chains of fairly rounded grains, which form an open, extremely high porosity framework. So the porosity can be up to 60% in some of these parts of the layers. You can see these chains of grains here. There's another chain there, and then there. It's very, very striking. It's really, really remarkable when you see these open chains. So we need to address all of that. How do chains form? Well, chains of spinel, whether it's magnetite or chromite, are actually really common in basaltic igneous rocks. So this is actually a very thin sill from sky. It's very shallow in place, so it's got a fine-grained ground mass. And you can see these beautiful chains of chromites, and they're actually scattered all the way through this rock. This is a very common thing. Chromite does form chains. How? Well, the Campbell idea is heterogeneous self-nucleation, where you have a grain of chromite and then you nucleate another grain of chromite on it. The first grain stops growing, and this one then starts growing, and then another one will nucleate. And I put this goes against our physical and thermodynamic understanding of nucleation. That's a polite way of saying that if he brought that idea to a first-year undergraduate tutorial, it would have been demolished in a few minutes. It doesn't work, okay? So these grains must have nucleated elsewhere, either by primary nucleation, heterogeneous or homogeneous, or by secondary nucleation. And secondary nucleation is a process of nucleation which relies on already having a grain of that mineral somewhere in the system. Now, the easy way of understanding that, which was the sort of the primary explanation for secondary nucleation, is when you've got an industrial crystallizer and you're stirring it, and the phase you want is forming dendrites, and the stirring breaks off tiny little crystals or little seed particles from those dendrites, which then act as the nucleus, if you like, of other grains. That's what secondary nucleation is. Right, so why would they come together if they were nucleated elsewhere? Well, this is where we need to look at experiments and think about, you know, what's the physics going on in a process, where, in a system where we've got more than 2 grains of chromite. Now, these are some beautiful experiments which were done by one of Max Schmidt's students in his trilogy of compaction experiments. They're very, very lovely. So these are chromite crystals, and they're nice and rounded because they're texture equilibrated, so we can measure the dihedral angle between the chromites and the glass. And this is my work here. So the chromite melt dihedral angles, this is 3 or 4 different experiments. The median value is about 30 degrees. So it's a nice low dihedral angle. So this is just the force balance between the grain boundary energy, chromite grain boundary energy, and the chromite melt interfacial energy. And what it tells us is that the chromite grain boundary energy is less than half, less than twice that of the chromite melt interface. So if you've got 2 grains and they come together to form a grain boundary, what you've done is replace twice the area of the chromite melt interface by the chromite grain boundary. And that's actually energetically advantageous to do. There's actually an energy drop when you form a grain boundary between those 2 previously isolated grains. So all you have to do is bring them close enough together so they can see each other by van der Waals forces, and they're going to go kaping, and they're going to sinter together and form a grain boundary. Okay, so the synusis model is that they're moving around because of magma flow, convection, whatever. When they get close enough to another grain, they'll come together and sinter and form a grain boundary, because that reduces the total energy of the system. So if we have synusis of faceted grains of chromite, this is what we get. They are bound together on these 111 faces or 110 faces. Okay, they come together and form by synusis. There's lots of examples of this. So this is just from a chilled margin of an olivine ferric sill, again from the Isle of Skye, and you can see chains of olivine that have formed like this. So they're chains in 2 dimensions. They might be bigger 3-dimensional clusters. We don't know because we've only got a thin section. And they come together, and there they are joined on these planar growth faces. They were just nice euhedral grains. They came close together and bam, they sintered and they formed these clusters. You can also see them with quartz. This is a paper that Brendan Dyke wrote, where he was looking at the granites from Bushveld, and you can see clusters of quartz grains. And they've come together on growth faces and they've sintered to form clusters. And that was his argument, that we've got convection in that granitic system. And we can see the internal growth zones of the quartz using cathodoluminescence, so we can tell that they grew as separate grains and then came together to form clusters. So let's go back to the UG2. What can we see? Well, if these grains had formed those chains of beautiful faceted grains, like we see in rapidly cooled rocks that have just quickly emptied from a magma chamber, then we would expect to see many pairs of grains joined on their 111 faces, because those are the euhedral growth faces that we've got a chromitite. But we don't. So on this diagram here, these are 2 separate samples, and we've got, this is Zoja, we have got red and blue grains, and they're joined on their 111 faces. And you can see it's about 10% of the grain pairs are joined like this. So it's not the same as what we're seeing in lavas, the rapidly cooled rocks. These grains are not joining on euhedral, or they weren't faceted, clearly faceted when they joined. So the next question is, well, were they rounded before they were aggregated? If they were rounded, there wouldn't be any nice planar faces that could come and stick together. So if they're rapidly cooled, chromite will grow. Well, if it's really rapidly cooled, as we heard in the last talk, they're going to grow as dendrites. But we're not going to go into that diffusion limited regime. We're talking about interface controlled growth. They're going to be beautiful and euhedral. So that's basically what we see in many of these rocks here. The extrusive rocks, we see nice euhedral grains, nice beautiful octahedra. But this is one of these experimental charges, and we've lost that primary growth shape, because the primary growth shape is controlled by attachment kinetics, essentially. How quickly can we add these things to the growing grain? But if you let it sit at constant temperature and mull over its sins, then what it's going to do is reduce the total interfacial energy by rounding itself off. Okay, so every mineral will have its own minimum energy shape that is not necessarily the same as the growth shape. And clearly for chromite, it's not a nice spiky little octahedron, it's a much more rounded grain. So if we look in detail at the UG2, you see that these grains are very, very rounded. Look how beautifully rounded they are. They're really not that faceted at all. And in fact, the last talk set this bit of my talk up very, very nicely, because if we actually look at the dihedral angles in here, this is chromite plagioclase. What we see is that it's a much higher dihedral angle. It's no longer down here. It's now up with a nice unimodal distribution around 90 degrees. And that's because what we've had is subsolidus textural equilibration. So this used to be beautifully rounded. It used to look like experimental charge with a low dihedral angle of about 30 degrees. The melt was replaced by plagioclase, and the plagioclase chromite dihedral angle is not 30 degrees. It's probably about 90. It might even be as big as 100. And if you zoom in at these arrowed junctions, you can see there's actually the break in slope as you get partial textural equilibration and a widening out of that 3-grain junction. It's really very, very clear. There's a really obvious one right there. So this thing was formed of rounded grains in melt present textural equilibrium. Once it's solidified, you then got some modification. And that essentially, the fact that we've got this partial subsolidus textural equilibration tells us that it must have cooled really slowly. Subsolidus textural modification takes a long time. So I would argue that the reason we don't see lots and lots and lots of pairs joined by their 1-1-1 faces is because these clusters formed by the aggregation of rounded grains, because we were dealing with a hot system that didn't cool that quickly, and they were texture equilibrated. They were nice rounded grains. And not only that, but those pairs of grains that we've got are very, very similar in size, and I'll get back to that shortly. Right, so these are our observations. We're stacking them up now. We've got aggregation of rounded grains to form chains, making this open high porosity framework. Now, what happens once we've aggregated to form our chains? Now, this is just a little cartoon here. So if they just aggregate and then are immediately quenched, as indeed we have this is just a magma chamber that was just emptied out, made a little 3-meter sill, and then bam, everything just stopped. No post-aggregation growth. Then you're basically seeing the original shape of your chromites, and they're just stuck together on their 1-1-1 faces or 1-1-0 faces, and it looks a bit like this. Now, I don't have any nice examples of chromite doing the next stage, so here we're just going to jump to olivine. Okay, so this is olivine, and it's just formed its little clusters by synosis and joined on their growth faces. Now, were we to leave that cluster able to continue to grow, and the example I'm going to show you is from an olivine ferric sill, where those olivine clusters were kept in suspension by convection for a long time before they finally ended up on the floor. The olivine continues to grow once it's formed its clusters. And so what happens is this is like a caterpillar on steroids, right? It's just getting fatter and fatter and fatter. And the original diameter of the particle is shown by the small axis here, because it can only grow out sideways. And then small grains that are trapped or completely surrounded by other grains, they're just going to stay the same size. Okay, so this is what we see in the sill from Sky, where the olivine clusters were kept suspended for a long time. And you can't see it terribly clearly here, but I've drawn over some of them. So you can see that is the olivine shape there, but the original olivine would have been a tiny little round thing like here, but it can only grow out. So it becomes plate-like. Okay, so this is post-aggregation growth. It changes the shape from the original shape, but in predictable ways that are determined by where the adjacent grains are. Sorry, 2 more minutes. Sorry, guys. Okay, and the shape depends on the timing of the aggregation, right? So the later they are aggregated, the more euhedral they're going to be. Oops, I am going to overrun. And why is this doing this to me? Okay. So the recent work argues for this in situ formation of chains to form the framework structure. And it is reliant, although less so now, I think, on this idea of heterogeneous self-nucleation. But if the chains grew in situ by progressive addition of grains, we would expect to see some sort of progression of size, because you can't stop them growing once other grains have aggregated on top of them. Okay, so we might expect to see an overall fining upwards thing, but we don't. We don't see overall fining upwards, and we don't see any sort of clear progression of grain size along these chains. Now, what we do need, and this is where we're sort of losing information, is that all I can see is 2 dimensions. What we need is 3 dimensions. And this is where Steve Barnes and his amazing tomography needs to come into play. We need to look, see if there's any systematic change in shape or size along these chains in order to argue for the in situ aggregation. Right, so generally insignificant post-aggregation grain growth. We've got some ostrald ripening, which this is Ilya Wechsler's work, which says that, you know, once these chains had formed, or once the UG2 had formed, then we do have some ostrald ripening, loss of small grains, which we know is basically indicative of slow cooling in the melt. So yes, so we've done all this already. We've got slow cooling shown by ostrald ripening, slow cooling demonstrated by texture equilibrium, both melt present and limited subsolidus accumulation, equilibration, and I'm just going to rush through this bit. I think we do have evidence of accumulation elsewhere in the hanging wall, in that the hanging wall is an orthopyroxenite. It's formed of elongated orthopyroxenes with interstitial clinopyroxene, and the orthopyroxene shows a lineation. So we've definitely got some sort of current migration and reorganization of our orthopyroxenes, for sure, you know, just centimeters above the chromitite horizon. And what we also see is that the chromites form chains that lie on top of these current sorted orthopyroxenes. And I would argue, and Zoja as well, is that this means that those chains were part of the depositional assemblage, if you like. They were there as part of the crystal accumulation. So that gives us evidence of accumulation rather than heterogeneous nucleation on grains of other phases. So I'm going to pull this together. I mean, I greatly admired Zoja's talk yesterday, which you weren't all at, because at one point she said, I don't have a model, I've just got observations, which I think is exactly the right approach to take when doing this sort of thing. But I'm now going to step outside the box and say, right, let's put all this together. So this is one long sentence. I reckon that this chromitite, all the evidence that we've got, points to accumulation of single grains and clusters, mainly the clusters are rounded grains, so they're randomly oriented together, and they were aggregated by synusis in a dynamic environment, as shown by that lineated orthopyroxenite. But the final thing that people are going to jump down my throat on is say, what? This is a really open framework, right? If you have single grains of chromite and you drop them into a beaker, your porosity is going to be about 30%, give or take, depending on what your grain size variation is, because your small grains will fill in the spaces between the big ones. We've got a really, really open framework. But then you need to think, hang on a second, we're not dropping down single round grains, we're dropping down clusters and chains. And the packing efficiency of things with an aspect ratio that's not 1 is very, very sensitive to shape. So this is some beautiful work by Williams and Phillips from 20 years ago now, where they did random close packing using a computer. So the best possible packing you could get as a function of shape. So here's your aspect ratio here. This is just a close-up of this zone here. And you can see that the porosity, well, this is the packing density, right? This is the inverse of porosity. It drops precipitously once you've got more than 4 or 5 grains, essentially forming a chain. So this is the best case scenario that we've got. We're going to have low Reynolds number, in the magmatic situation. We've got particle cohesion. We don't have nice thin rods like this model here. So it's going to be even more sensitive to shape. So the accumulation of chains or random clusters is the way to get this very, very high porosity. So yeah, that's my conclusion. I think the observations all pulled together basically say that what we're looking at is a magmatic sediment. Thank you.
I'm so proud that I'm part of the story. And always part of the proud to be working with Marian. Well, can you have some questions or no? I don't want to keep you away from your lunch, sorry. Right, that's all your head.
Well, I certainly disagree with you, because Marian, 100%. And but there is something which I really would like to say about these clusters thing. I think there's a very big problem which needs to be resolved with these clusters. Because our magma, basaltic magma, contains 0.0 whatever chromite, so the very, very low amount of chromite. So if you imagine the saturation of chromite in the big magma chamber, where you would like to settle, so then perhaps we can imagine that one chromite will, where one chromite grain will be where you are, another one will be another part, and then, and here. And if magma will circulate, laminar flow, then there is, I think there's a great chance that these crystals will never meet together, will never bond together to produce clusters. Of course, that's just gut feeling, and that needs to be real modeling to check such kind of thing. But that's, I think, is a very big problem for any clusters, apart from the fact that you cannot settle chromite clusters on the cuttings and all kind of things. Thanks.
Yeah, but clusters are actually very common. I'm trying to find the slide where I've got them, that nice little chain of chromite clusters in my my thin sill. I mean, they do form, and you get clusters in almost every basaltic rock I've looked at, erupted one. There are clusters of magnetite grains, clusters of chromite grains.
Yeah, I think the medium in the dike, that's fine, but in the magma chamber, that's different.
So I totally get the point that the chemistry side of these chromatites is a nightmare, and I leave that for better chemists than me to look at. I'm just going on the microstructural observations of now. Steve?
Marian, I always find your talks fascinating,
But
yeah. So this bit about the crystals become rounded to reduce the surface energy. Crystals can also become rounded as you dissolve them, and they can also become rounded as you abrade them. And given that Manucheri and Schmidt milled the chromitite before they did the experiment, isn't that why they rounded?
no, because they sent me the photographs and the time sequence. So the ones that they experimented with the short time sequence were nice flat stick, and the ones that had gone on for another week, they've gone rounded. So we're looking at texture equilibration in that.
So despite the milling that they did, they still had the facets.
Well, that's because they improved really quickly in the first day or two of the experiment, and and then the facets round. What's the quiz? You then go to text. Driving force is smaller, it takes longer, but it will get there with a chance. So it goes to minimum energy change.
Okay, thanks.
A great talk, Marian. That's really, really fascinating. Would you mind? Could you go back to the slide where you showed the orthoperoxenite with the little chromite chains in it?
Yeah, can you find that? I don't know how to do this. It's all a bit too complicated. Oh, okay. Which one was it?
It was a few slides from the end. It was the hanging wall orthoperoxenite with little chromite chains in it. Yeah, that's the one.
Yeah.
Yeah, we've got some tomography on basically that rock type, not from that cycle, but it's essentially the same rock type.
Yeah.
What we found was that the size, I think the sample we looked at has probably got a little bit more chromite in it than that, but not much. What we found is that those clusters are actually up to about 2 or 3 centimeters in size. So they're several, like up to about 10 times the size of the orthopyroxene crystals.
Which section do they go in?
They're more or less parallel to the foliation like you've shown there. So, I mean, it is possible perhaps that they could be accumulating, but I think it's hard to see how it works. But I think I think what would be really interesting would be to do one of those simulations that you showed from I think it's the Philipsa paper, to do one of those simulations actually taking those shapes and the orthopyroxene phases. And I think there's a lot of opportunity for some smart graduate student could really make a name for themselves by doing some of this kind of stuff, because the particle codes exist for doing all of this. They've been around for years. And they're relatively commonplace. So there's a huge potential for I think really answering some important questions.
Yeah. And what I would like that very clever graduate student to do is also use your 3D tomographic imaging and see what spatial patterns there are and what directions they go. That would be an amazing thing. That's the next thing we have to do.
Absolutely.
I agree very much, and that would be told. And I would like to refer to the second talk today, where a crystal mesh comes probably into the system. But what we have observed in the Karim in the model chromitite, that there's a difference in grain size in the chromites included in the plagioclase oikocrys, smaller than the ones in the pyroxene oikocrys, smaller than the ones in the logopite oikocrys, which are, and the chemistry is going to change, and it's a night, but a solution.
I would be very interested in looking at that, because that seems to be entirely great for its possible ripening. And John Lundy mentioned the fact that if you're dissolving a crystal, you make it round. And what the signature for osmotic ripening is that the grains below the critical radius, the ones that are dissolving, are rounded, and the ones that are actively growing are faceted. So what you would do is you would look at the shape of your crystals as a function of size in your different oikocrysts and see if you could pick out the point at which osmotic ripening started to be important. That would be a really nice thing to do.
Other point is that you can just come to the poster session, and there's a very nice example for that.
I saw Katie. So Wolf said continue, so we're continuing.
Just a little bit more.
Thank you. I've written copious notes. Thank you very much. I was wondering if you'd ever, if you've ever used EBSD to look at whether you've got distortion and misorientation at the chromite interfaces that you don't see. I'm sorry, I probably.
This is Zoya's answer.
Yeah, so I probably missed that bit of the literature.
During the lunch.
Okay, sounds good.
So did you mean the grain boundaries or deformation within the chromites?
You would if they've kind of been doing stuff while they're connected, you would expect to see different things at the chromite interfaces.
Schematics in the grain boundaries. So
yeah,
that's the different coincident side lattice boundaries as well, not just twins. We tested twins, how common they are. There is no systematic.
Excellent. I'll ask you at lunch, which will happen.
And we can now stop and have lunch.
Let's come back at 1:15, so we are a little bit delayed. It doesn't matter. Just carry on with the ball. 1:15, 1:15.
I was thinking if I go, I continue on to your talk and then you can take over a bit. You're done. No problem. It's because you want to. This one? I don't know, but. And here I can put where? Let's see, I think it's this one, the for July. They do. Okay, so if you open.
Good.
So just get the line. This one, please. I removed a couple of slides, you know, I think we should just look at number, yeah.
We also have Willem's talk now, finally.
It's